says we're going to select 3 different coins, and we want to measure the diameter of each of them separately with units and uncertainty. All right, so I'm just going to draw the setup. All right, but we're going to call this distance D1, this can be D2, and then D3. And the whole point of this is to place them all in a row in a straight horizontal line with their diameters touching each other. And we want to calculate the distance D1 plus D2 plus D3 across all the 3 coins. All right, so I got a ruler for myself to just measure this diameter of the $50, right? So I measure 3 centimeters across, but my ruler is marked to the millimeter. Okay, so when I give my distance, I can't just say like 3 centimeters. That's not enough information according to this ruler. Like, this ruler should allow me to give a 100th digit. Or I could make it perhaps 30.0 millimeters. Because it's marked to the millimeter, so I have to go 1 digit beyond is the idea. Now, I should also give an uncertainty to that though. So how far off might I be? I might be off by as much as 5/100ths for my $50. Okay? I just want to measure the other coins in the same way. So the quarter to me is like 2.39 perhaps centimeters. Plus or minus 0.05. And then the penny, yeah, 1.87, I think. All right, now what we want to do is add the measurements together. And there are rules for adding and subtracting with sig figs, right? So one of the methods I use is to add them up according to the old grade school way, adding them vertically, I mean. You want to line up the decimal places and line up all the place values so that you have your ones in one column, and you got your tenths, and you got your hundredths. Alright, just add them. Now, according to calculator, the result is 7.26. And so far, I don't have to make any adjustment to that when it comes to the sig figs. The reason why is because we have significant digit information in the first column, and in the second column we have significant digits, and in the third column we have significant digits for all the measurements involved. What that means is that all my final results are going to be significant as well. So I want to keep those in my final answer. Alright, but here's the hard part. How far off is my final result? Like, how much uncertainty is there? So a lot of times people assume that since the original measurements had 0.05 centimeter uncertainty, and that's what, my final result should have too, but that's not right. Instead, we can do a couple of different methods of analyzing it. One would be to calculate what's called a best estimate. And then we can calculate a smallest estimate and a largest estimate. This is just one of the ways of analyzing the uncertainty, right? So the best estimate comes from just adding the numbers together. So that actually gives us 7.26. We already did that one. But how do you get the smallest estimate? Well, what you do is you would subtract the uncertainty from each measurement. So you take your 3 and then subtract 0.05 to get the smallest that the $half could be. And then take your quarter, subtract its uncertainty, and you get the smallest diameter that the quarter might have there, and do the same thing for the penny. Alright, let's see what that gives us. That gives us 7.11 centimeters as our smallest estimate. And remember, the best estimate was 7.26. So you can see how different they might be, is the idea. And then do it with the largest value by adding the uncertainties. $7.41. Alright, so the idea is behind this that there could be a wide range of different results for our final calculation, right? So the best estimate goes in the middle, 7.26, and we might go as high as 7.41 with that sum, or as low as 7.11. Here's the largest. This is the smallest. Now, in order to get a good estimate of the uncertainty in the final result, we could just subtract, because we want to know how wide this confidence interval is. It's called a confidence interval for our calculation. So if we just do best minus smallest, we can get that result. Or we could do largest minus the best. And then that can give us our uncertainty. So 7.26 minus 7.11. Or we could do 7.41 minus 7.26. You get 0.15 here and 0.15 there. So it looks like the best estimate of the uncertainty then would be 0.15. Now this could be okay here as a final answer. Notice though that we have 2 digits in our uncertainty. A lot of times we want just 2 or 1. 2 is acceptable though, but generally you don't give more than 2. So I'll leave it like that, and that'd be a good final answer.